Hello, this is Dr. Hawkins again. I wanted to work through some of the examples or some of the problems, a few example problems that I had assigned you. I'm not going to work through all of them because I don't want to take that much time, but I will, if you have a particular one that you have a problem with it, uh, that you don't understand, email me that problem and I will work it out for you and send it by email or post another podcast or something. But I will play requests, so to speak. But for now, I've selected a few that I thought were particularly instructional or maybe a little difficult for one reason or another. One, I couldn't get the answer they got in the solution, so I definitely included that one. I'll show you my solution part. I don't know if the other guy's wrong or if I'm wrong, the one that did the solution. But these can be very tricky, to say the least. Let's start with number 6. This will be Boolean. Boolean algebra problems. I want to start with number 6 out of the homework set that I gave you last week, which was due last night, by the way. And if you hadn't finished, don't quit. Keep trying on them. I hadn't given you a quiz on it yet. I probably will in the next day or two, a homework quiz. All right, this one starts out with the expression A or A not B. And we're going to use a law that they call the absorption law that looks almost like this, except it doesn't have the not. Let's just go ahead and do the absorption law off to the side here, and then we'll come back to the original expression. The absorption law says A or AB without the not. You can factor an A out of that, and anything or 1 is 1. So the expression inside the parentheses equals 1. And so A times 1, or A and 1 is 1. So this expression here reduces simply to A. And we're going to use that up here in this original problem. I'm going to replace the A here with this because they're equal, right? So that's going to give me A or AB. Or A not B. That's equal to this expression, of course. Um, now I can factor out a B from the second two terms, and that's going to give me A or B times A or A not. Well, anything or its inverse has to be 1, because if A is 0, then A not is 1, and 0 or 1 is 1. If A is 1, then A not is 0, and again, 1 or 0 is 1, so that gives me 1 times B, or finally, A or B. Let's look at number 9. It's an old Beatles song, actually. A not or B not. And A not or B. Another thing I want to point out here, and I'm not going to give an example of this, but many times these different problems the same problem may have 2 or 3 different type solutions, 2 or 3 different paths that you can take to get to the same solution. So you may have a different way to work some of these that works out just as well. I don't know. This is just the way I chose to work this one. Just like in regular algebra, when I have 2 binomials ANDed together, AND is equivalent to a multiply in regular algebra. So we can use the FOIL method to multiply that. What does FOIL stand for? It stands for take my 2 first terms. I have my pointer here. There's a first term there and a first term there. So I'm going to AND those 2 together. And that'll give me A naught, A naught. Or now we're going to take the O stands for outside. So outside is that one. Whoops. That one. And that one. Those are the outside terms. So that's going to give me A naught B. Or I stands for inside. So these are my 2 inside terms here, the B naught and the second A naught. I'm going to reverse them though to keep them in the same order. We do have a commutative law, which means if I'm ANDing or ORing, if I have, let's just forget the knots for a minute. If I have A and B, that's the same thing as B and A. If I have A or B, that's the same thing as B and A. And then finally, my 2 last terms, that's the B naught and the B. So there we have the FOIL. We've multiplied out the 2 binomials. Now 2 of these terms are easily reducible. Anything or anything and itself is itself. If A is 0, then A naught's 1, or 1, and 1 gives me a 1. If A is 1, A naught is 0, 0 and 0 is 0. So anything and itself is just itself. And then we've got my A naught, which the next 2 terms together we can factor out in A naught. So let's go ahead and do that. That's just out of these 2 terms. Factor out the A naught, and that gives me a B or B naught. And then finally, anything and its complement is 0. If B is 1, B naught is 0. 0 and 1 is 0. If B is 0, B naught is 1. Again, 1 and 0 is 0. So that last term just is 0. So now, again, we have the idea of anything or its complement is 1. Because 1 or anything is 1, and if you get the B and its complement, one or the other one has to be 1. So that leaves me A or A naught. And one more time, anything or itself is just itself. Okay, let's go to the next one now. Let's see, I've got number, I believe it's 11. Now they make a statement right above 11 regarding problems 11, 12, and 13, and it says that f of A, B, and C, f of A, B, C is going to be A or B or C. That's just a definition they made for those 3 problems. So in this case, they give us f of, where did I hide it here? Here we go. F of A, B, A, B. That'll be A or B or AB. And let's see, what can we do with that? We can, well, we could do an absorption law there. Let me look at this, see what I did on my notes here. You could do absorption two different ways, really. You could use the absorption on that one, or you could use the absorption on those two. Remember, absorption says A or AB equals A. So I did it the other way in my notes. I just noticed this. So B or AB would be B. So we simply get A or B. Again, there's different ways you can do some of these and still come up with the same answer. Hopefully the right answer. But these can be tricky. I understand. They're tricky for me sometimes too. I read somewhere, I guess when I was a student at Mississippi State 30 odd years ago, and I was taking a digital devices class. It was the first time I ever encountered this material. And according to that professor, at least, this algebra was developed by a man named George Boole. He was a professor, I believe, in Ireland, but he had connections to the British Queen's Court. This was during the time of Queen Victoria. And this became a popular pastime. People would sit and do Boolean algebra problems for fun. So, I don't know. Let's look at number, again, I've written over the number on this one. Let's see if I can read it back. Anyway, you can look up and see which one it is. I'm not going to take the time to dig it up myself right now during the middle of a podcast, and I don't like switching these things because it breaks it up into multiple podcasts instead of just giving you one continuous one if I try to pause it. But anyway, this looks like 19 if I can read my writing correctly. So I'm going to go ahead and put that with a question mark. And it starts out with W or X naught. Got a parenthesis there. Or Y or Z naught. All ended with a Y. And so what I did is I went ahead and distributed the Y through the parentheses. We do have the same, I mentioned commutative, we have the same associative, commutative, and distributive laws that we have in regular algebra. They all still work here. So if I take Y and multiply it, I have to multiply it by each term in the parentheses. So I'll have a YW or YX naught or YY or YZ naught. Now, the YY term, remember anytime anything ANDed with itself is itself. So this becomes just a Y. So I can rewrite that Y, W, let's not factor yet. I'm going to factor the y back out in a minute, but let's go ahead and write it out this way first. And again, I'm getting ahead of myself. Let's put this y out in front for yw or yx bar or yc bar. Now I want to factor the y back out of everything, and that's going to leave me with y, and that's going to give me a 1 or w or x bar or c bar. And remember, 1 or anything is equal to 1. So that entire expression reduces simply to just a y. Now they use w's, x's, and y's here. We've used a's, b's, and c's before. It don't matter. There's variables. We can call it p, q, and m if you want to. Any numbers or Greek letters or anything you want to pull out, you can use those. In the class, I'm mainly going to stick to the A, B's, and C's, but you do need to realize that we're not just limited to that. All right, I want to do one more, and this is the one I didn't get the same answer that they got. I think they made the mistake, but it's always possible that maybe I did. This is number 26. This may end up taking more than a page. I'm going to look through it on my notes here. I've got an X or Z and X naught or Y and Z or Y. All right, so they didn't really show, and they don't on these solutions that I gave you with the homework set. They don't really show the details of everything they did. They just show some major steps, maybe, or in some cases, just the final answer. But apparently what they did, and what I'm going to do, is they used the FOIL method again to combine these two parentheses and just held this one back for a while. We'll save it for later. We will use it. For a while, we're just going to copy it on down and work with the other two. All right, so my first gives me a x naught z. And when I say first, now again, I'm dealing with these two terms now. So there's my first, one first, there's my other first. I'm going to do outside, get my dot to show up. There's the outside, there's inside, and then y will be last. So I'm not going to stop and point those out every time like I did the previous example. Anyway, I get an xv from my first, then I get our x naught z, then I get an x naught y, or yz, or yy. And of course, that one becomes just y, because anything or itself is just itself, right? So let's see what we can do to reduce this. I factored out the y in these three terms. I didn't close my parenthesis over here. So that's going to give me, still got to bring down the x or z. We hadn't dealt with that one yet. And that's going to leave me an x naught z, or y. I'm going to do this term first. Y factored out of that just gives me a 1. And then that's going to leave me a or x naught or z. Again, 1 or anything is 1. So all that reduces to 1, and 1 or y gives me a y. So that gives me, and down my x or z one more time, x naught z or y. And I don't have the homework set in front of me, but this is their final answer, except they were missing either the z or the x naught. I don't remember which one. And that was as far as they could get. I think it was the z that they lost somewhere in the shuffle, which I don't see how they did that. So this is what I get if I go just as far as they did. Now we can go the one step further and do FOIL again on these two terms. That gives me x naught z for my first, or my outside gives me x y, or my inside gives me z x naught z, and then my last gives me yz. So we can reduce this a little bit further. X or x naught gives me 0, or x and x naught gives me a 0 for that term. And z and z gives me just a z, so that'll be xz there. X naught z. So what I got for the final answer is xy or x naught z or yz. Now you could do a little bit of factoring there too. You could factor out the y from the x or z term, or you could factor out the z from the x or y term and show it different ways. But if you're thinking in terms of doing a ladder logic diagram out of this, there's really not a whole lot of point in it. So we may not always want the absolute simplest form when we're doing ladder logic. We want the one that fits the ladder logic the best. And I think this one would fit better than the other way. Again, now, if you have any questions on this, email me. If there's a particular problem that you had trouble with or didn't understand, I don't just say, hey, how do you do this one? Show me what you did. Write me an email and show me where you attempted the problem, what you tried to do, and why you think there's a problem with it. And then I'll see if I can't figure out how to help you with it and email back. Or maybe if it's enough to warrant making another podcast so everybody can see it, I might do that too. Now, I'm about to assign you a couple of websites to go visit. They'll be in a separate announcement from this one, but they're both dealing with something that we call Carno maps. Let me just go ahead and write that out one time too. Also called K-maps for short. K-map is a graphical way to reduce Boolean algebra expressions and simplify them. The Boolean algebra rules that we've been practicing on for the past few days, again, can be very tricky. And what we do with a K-map, I'll show you the 3-bit one to begin with. We draw a grid. Where this is maybe A, B, and C. And then we label each of these boxes. This is the C direction here. So this is C naught. Everything on that row is C naught. Everything on this row is C. And these we label 0, 0, 0, 1. Now here normally we go 1, 0, and then 1, 1 if we were counting in order, but they don't do that here. They use what we call a gray code, where you only change one bit as you go from one step to the next. So here they go ahead and put the 3. So this is 0, 1, 3, 2. And everywhere there's a 0 in the A position, that column is A naught. Everywhere there's a 1 in the A position, that column is A. Everywhere there's a 0 in the second position, that's B naught, that column and that column. So let me get my pointer back out where I can illustrate that. Well, we can do it this way. This is C naught because C gets a 0 there, that whole row. This is C. All right. Here, the two left-hand columns are both 0 for A, so that's A naught. And the two right-hand columns, A is 1, so that is A. This will make more sense when you start reading through some of the material, but this is something they didn't explain really well when I was reading through the website. And again, I'm going to do a whole lecture on this soon, in the next couple of 3 days. So here are the two middle columns. B is 1, so they're both B. And the two outside columns, B is 0, so those are considered B naught. Again, I don't want to go too far with this today because I'm going to do a whole lecture on it in the next couple of days. We'll go in more detail. This is a 3 variable. We got A, B, and C. You can do 4 variables, A, B, C, and D. You just have 2 more rows. You can do a 5 variable or more, but once you get above 4, it starts to get a little more complicated, but you can do it, and I will show you that in the next lecture. Again, if you have any problems, please shoot me an email, and I'll do the best I can to resolve it for you. Until the next lecture, please go read over those 2 websites that I mentioned that are dealing with this Cardinal map stuff, and we will carry on from there.